Okay, this will be part 4 of the series where we find intervals where a function is increasing or decreasing. And in this fourth part, on the fourth example, we'll look at a function that is a rational function that has asymptotes. And we'll see how the asymptotes affect how you go about the process. Now, here's the same steps that we've defined in the previous 3 videos. And if you have not done it yet, I want to emphasize, definitely watch part 1, which will describe where these steps come from. And if you watch the part 1 video, then this video will make a lot more sense. So as we go through this, I'm going to assume that you've watched the part 1 video and you're familiar with these steps. So with this in mind, let's take a look at a function that has asymptotes. Now the function itself will be this one right here. So f of x is equal to x squared divided by x squared minus 4. Now normally we would start by the following series of steps. If you wanted to find the critical points, you'd find the first derivative, set the critical point equal to 0, find out where it's undefined, and find critical points, which would allow you to divide it up into intervals, as we did in the first 3 videos. But in this one, there's one extra step we'll put in first. Now the idea on this is this. If you have an asymptote in a function, then the function's undefined at that point. Now, to find where the function is undefined, it occurs wherever the denominator is equal to 0. So to find the asymptotes, go ahead and take the denominator, set it equal to 0, and solve for x. So what we'll do here is we will find, very first step in this one is find the asymptotes. So we want to find the asymptotes to the graph. And to do that, take the denominator and set it equal to 0. So x squared minus 4, set that equal to 0 and solve for x. So x squared would be equal to 4. X would be equal to plus or minus the square root of 4, which would give you x is equal to plus or minus 2. So you get x is equal to either a negative 2 or x is equal to a positive 2. And that's where the asymptotes will be. So what I'm going to do is go ahead and put that on the graph right now. So I'll come over here, and this is going to be a negative 2 right here, and I'll say about right here, I've got a positive 2. Now again, for an asymptote, I'm going to go ahead and put a dotted line through here. So I'll put a dotted line that goes like this, and this dotted line will represent an asymptote on the graph. And I'll do the same thing right here. So I've got to come over here, put a dotted line down through here, and I've got an asymptote in the graph. So here is an asymptote, and here is an asymptote. Now, strictly speaking, if you go by the rules, an asymptote is not a critical point on the graph because critical points exist only where the original function exists. And the original function is undefined at an asymptote, so strictly speaking, it cannot be a critical point. But it can function as a critical point. And by that I mean the graph might switch from increasing to decreasing at these points, so we'll consider them in that light. So we've got the asymptotes on the graph. Now what we'll do is go back and follow the steps that we've done for the other examples. So strictly speaking is this. Now we need to find the first derivative of this thing, but this is the first example that we've done where you're going to have to use the quotient rule to find that. So let's go back and try that. So step number 1 is to find the first derivative. So I've got step 1 over here, which is to find f prime. So I want to find the first derivative. But to do that, I've got to use the quotient function. So what I've got is the first derivative of this thing. Now, the quotient rule says that it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So we'll go ahead and put that on here. We'll put a bar across here, and it looks like this. Now what we've got, it's the original denominator, so it'll be, there's the denominator, then times the derivative of the numerator. Well, the derivative of x squared would be 2x. Then you've got a negative, then you've got the original numerator, and I'll extend this line just a little bit. So the original numerator times the derivative of the denominator. Well, the derivative of the denominator, this will be 2x, and the derivative of a constant is 0, so it turns into that. And then this is all divided by the denominator squared. So that's the quotient rule. So we'll go ahead and run through the algebra to finish this up. Now, first thing you have to do is to distribute this 2x. So 2x times this and 2x times this. So this is going to give you 2x cubed minus 8x, and then multiply these two together and you'll have minus 2x cubed. And again, the whole thing is over x squared minus 4 quantity squared. Now you'll notice that these two will cancel out. You've got a 2x cubed and a minus 2x cubed. Those two cancel out. And that's going to leave you with this, f prime of x. So f prime of x will be equal to a negative 8x over x squared minus 4 quantity squared. So this is the derivative. I'll go ahead and put a little box around this thing right here. So here is the derivative. So now we've got the derivative. Let's go back and take a look at the rules. So we've got step 1 done. You found the derivative. Now to find any critical points, you can set the derivative equal to 0 and solve for x. So now also you could say this, that you could also have additional critical points where the first derivative is undefined. Now again, this gets you back into that strictly speaking rule. In this case, if you were to plug a 2 into the denominator, then the first derivative would be undefined. So some people make the argument, well, in that case, then it would be a critical point. But again, the critical points only exist where the original function is defined. It has to actually be a point on the graph. So the asymptotes will function, they will act like critical points, even though they're not really critical points. But what we want to know is this. We want to know where is the first derivative equal to 0. So what we'll do is this. Take the first derivative and set it equal to 0. So we'll take this thing and set it equal to 0. Now, if you have a fraction and the whole fraction is equal to 0, the only way that can be true is if the numerator is equal to 0. So this means that minus 8x would be equal to 0. And if you solve this, you will get, that's only true if x is equal to 0. And what this does, it gives you a critical point on the graph. So when x is equal to 0, the first derivative is equal to 0. So this will be a critical point on the graph. So what I'm going to do is go back up here, and I'm going to actually plot that point now too. So this would be 0, and this is going to be a critical point on the graph, and I'm going to have a horizontal tangent where f prime is equal to 0. So I know I'm going to have a horizontal tangent at that point. Okay, let's go back and take a look at the rules now. So what that does, that gets us into truth step number 2. We found set the first derivative equal to 0 and solve for x. Step number 3 says use this to divide the graph up into separate intervals. So we'll go back up and do that. And actually, what I'm going to do is go ahead and I will put an interval right here. So this interval is going to go at the critical points. We'll have a point where it can be divided into an interval. So from here, and I'll say down to about right here. So now what the intervals look like is this. You've actually got 4 intervals. You've got one interval that goes way out here to a negative infinity, way over here to a positive infinity. So the intervals would be this. The first interval goes from here to here. So from negative infinity to negative 2. The second interval would be in here. The third interval would be in here. And finally, the fourth interval would be out here. So whenever you're working with asymptotes, you can treat the asymptote, it behaves as if it's a critical point, even though by strict definition it's not one. But it divides it up into 4 intervals. So now we'll go back and look at the rules again. We've got it divided up. So the next step in the rule says this. Pick a convenient test point inside each interval and evaluate the derivative to see if it's positive or negative. If it's positive, it's increasing, negative, it's decreasing. So we'll do that. So what I'm going to do, again, to pick a convenient test point, I like to work with integers. So I'm going to pick in this interval a -3. In this interval, I'll pick a -1. In this interval, I'll pick a +1. And in this interval, I'll pick a +3. So now what I have to do is to evaluate the first derivative at each of those points. So that's going to be, and we'll go back and look at our rules again, step number 4. So what step number 4 will be, and we'll go ahead and put that right here, says this: evaluate the first derivative. I think I'll put a little bar to separate these. So this one will go from here, and we'll separate it kind of like this, down like that. Okay, so first of all, evaluate the first derivative at -3. So f prime at -3. Then evaluate f prime, first derivative, at -1. Then evaluate the first derivative at 1. And then evaluate the first derivative at 3. And all we're interested in here is whether they're positive or negative, just like in 3 into the first derivative on this. So this is going to be a -8. So we'll have a -8 here. So -8. And in place of x, go ahead and put in a -3 divided by, and then in place of the x squared, put a -3 squared minus 4, and the whole thing will be squared. Now, rather than running through all the numbers on this, what I'm going to do is this. Looking at the top, if I multiply a negative times a negative, I get a positive. Remember, I'm not concerned with the number, just whether it's positive or negative. And in the bottom, no matter what you plug in here, when you square it, it's going to be positive. So that'll turn into a positive divided by a positive, which is a positive, which tells me that the function is increasing. So on this interval up here, it's actually increasing. And it will be increasing on the interval from -infinity to a -2. So it's increasing in this interval right here. Now let's find out what's going on in this interval right here. This time plug in a -1. So I've got a -8, and I'll plug in a -1 divided by, in parentheses, a -1 squared minus 4, the whole thing squared. Now again, in the top you've got a negative times a negative, which turns into a positive. And then in the bottom, no matter what you put in the bottom and you square it, it'll turn out to be positive again. Positive divided by a positive is a positive, which again tells you that it's increasing in this interval. So it's going to be increasing in this second interval right here. And that's between -2 and 0. So it's going to be increasing from -2 to 0. Now, in the third interval, what's going on in this interval right here? The test point will be 1, so I'll plug a 1 in. So I'll have a -8 and plug in a 1 divided by 1 squared minus 4 squared. Now on the top, you've got a negative times a positive, which will give you a negative divided by, the bottom again will always be positive. A negative divided by a positive gives you a negative. So the first derivative is negative, which tells you that it is decreasing in this interval. So it's going to be decreasing in this interval here. So it's going to be decreasing between 0 and 2. So from 0 to 2, the function's decreasing. And then finally, in this last interval, let's go ahead and plug in a 3. So it'll be -8 times 3 divided by 1 squared, or pardon me, a 3 squared. 3 squared minus 4, the whole thing squared. Again, following the same arguments, a negative times a positive, I'll have a negative in the front, or in the top. The bottom one will always be positive. So a negative divided by a positive gives you a negative, which tells you again that it's decreasing in this interval right here. So it'll be decreasing from 2 out to a positive infinity. So from 2 out to a positive infinity, it's decreasing. Now what this does, this actually gives you the answers that you are looking for. So what you want to know is intervals where it's increasing or decreasing, and we'll just go ahead and put a box around this thing. So it goes from here down to here. and then across like this, around like this. We'll just put a little box around the answer. So the answer would look like this. And so you've now identified the intervals where it's increasing or decreasing. Now again, you don't have to do this, but in the previous examples, we've always sketched the graph. So if you did the graph, here's what this thing would actually look like. Now in this interval, it'll actually wind up, you can tell, since you've got an x squared in the top and an x squared in the bottom, you'll have a horizontal asymptote at the ratio of those coefficients. So you'll actually have a horizontal asymptote at 1, but basically the graph does this. It's going to be increasing in this interval, so it has to do this. It has to be increasing and curve up and approach but not touch the asymptote. So it'll go something like that. Then in this interval, it also has to be increasing. Now, you have a critical point with a horizontal tangent. So at some way, it's got to hit a horizontal tangent right in here. So I have a horizontal tangent right there. So horizontal tangent right here where f prime is equal to 0. So the graph has to be increasing and approaching this asymptote. So it's got to come up like this, level off just for a second, and have a horizontal tangent right there. So it'll go down like that. Then in this interval over here, it's got to go back and approach that asymptote, and it has to be decreasing in this interval. And then finally, in the last one, it has to be decreasing again. So from the asymptote, it has to go down, and it will look something like this. So if you graphed it on a graphing calculator, that's what the graph's going to look like. And what you'll see is you have a local maximum right here, but there is no maximum or minimum at an asymptote because it goes off to infinity. So that's an example of how to handle functions that have asymptotes. The only real difference is find the asymptotes, and you can treat the asymptotes in a way as if they're critical points because they will possibly have a change from increasing to decreasing. But strictly speaking, again, an asymptote is not a critical point because the critical points actually have to exist on the graph, and an asymptote doesn't do that. So there's an example of a function that uses asymptotes.